the cloud. There. So welcome to our March 2022 version of our monthly meeting. And thank you for being with us tonight. We've got another great program again. We're looking forward to, and real quick, I'll let's let Stephen, if he's still with us, give us a repeater update. Go ahead, Stephen.
So I have been doing some research on perhaps rebuilding the voter system. We had a repeater committee meeting not too long ago, and we had some action items from that. We've got a Raspberry Pi up there that needs to be replaced. Probably, I don't know if I can do it this weekend, but I don't know if Jeff can or not. But if he wants to, he's more than welcome to.
Yeah, I could go do that.
Okay. And
I gotta send Kevin an email.
All right. And then I've heard we also had some repeater problems. I believe it was on the net the other night, although I wasn't around for it. I heard it was some interference type problems. So we're going to have to get to the bottom of that.
Yeah, we had that interference we've had in the past, and it was during the marathon in the afternoon. Some of the same stuff we've had in the past. So that's what I'd mentioned to you. That may be what you're thinking of. So Barry, I think it's Barry is how you pronounce his name, Kane. I'd given you his number, so certainly reach out to him, and you might be able to get some help from him on stuff in the repeater committee and all that. So
yeah, I'll give him a call tomorrow.
It was kind of some of the same kind of interference we were getting with our nets, Sunday night nets there months ago. So unfortunately, same sound and everything. So it's coming back, whatever it was. I can't remember what the issue was back then, but I'm only 53, and you don't need to be 90 for your memory to be going. Mine's already going. So, but all right. Anything else, Stephen?
I think that's it.
All right. Real quick, of course, a few of you may have heard this all kind of took place really quick, but we have the 100th anniversary of the WSB radio station coming up March 15th. So a couple of us have managed to put together a special event for it. It's going to be a call sign W5B. It was about all that was available, and of course it works because the 5 looks like an S and between the W and the B, so we're going to be able to play with that on the QSL card a little bit. But it's going to be a week-long event starting midnight Saturday the 12th and running through Sunday to midnight Sunday or 11:59 Sunday, and all that work will be done from home. The only in-person thing we're going to do is on the 15th. We're going to have 2 stations, one at WSB for a few hours in the parking lot at Peachtree Street, and the other one will be an all day at the transmitter site out in Tucker. So as a club member, you're more than welcome to join us in one of those 2 areas, or to operate one of the bands during the week. If you go to at the bottom of this sheet here, you'll see a address, atlantaradioclub.org/WSB-100-event. And you should have received an email with this in there today. If you'd like to operate the event during the week as an operator, please go to that, and there's a link at the bottom, and you can click on that, and you can actually sign up for a time slot all week long, except for Tuesday. That's all blocked out because that'll be where we're out there at the actual event. So please do join us and participate in that. There's probably going to be a nice participation certificate that the operators will get after it's all said and done. We're going to try to get it signed by somebody special if possible in this whole thing. So it might be worth doing it just for the certificate, other than having a lot of fun doing it. So take a look at that and sign up for a time slot for that. It's going to be a lot of fun. And like I said, this was kind of put together really quickly. I didn't even know that this year was the 100th anniversary until somebody brought it up. Unfortunately, we didn't have a whole ton of time to plan for this, but I think we've been able to put it together all things aside. So the only other thing is this weekend, the Atlanta Radio Club is going to be out at Brook Run. We're going to be doing the International DX contest, and we'll be out there from about noon until dark. And Brook Run is in there in Dunwoody, there off North Peachtree Road before you get to Tilly Mill, I believe. And if you come in the main entrance, we're back in the back near the Treetop Quest, and we're either usually on the hill above that or in the parking lot pavilion right before you get to that. So, of course, we'll have talk-in at 146-820. If you can't find us, give us a shout and we'll direct you. So please consider joining us on those two events. Let's see. I think that's all I need to really bring. I was going to bring up since we had people here and everybody's attention. I'm going to turn it over to our handsome and dashing program chairman, Rob O'Sutton. Oh, and don't forget, tomorrow, Friday, is our usual lunchtime from 12:30 to whenever at Mellow Mushroom, Brookhaven. Please do join us for that also. Take it away, Rob.
Thanks, John. Let's make sure I'm unmuted here. So yeah, we've got another great program this month, if I do say so myself. We haven't had many programs from local people. Been taking advantage of the fact that, you know, Zoom people can get to us from all over. So I've been having national speakers, but we've got plenty of speakers here who are on that level. I haven't been going to them. So Tom, who lives in Stone Mountain, where I used to live in Buckhead, he's a local speaker, can talk to us all about amateur radio astronomy. And Tom, I was looking at trying to decide whether that was amateur space radio astronomy or amateur radio space astronomy. Just see.
Well, we'll start out with what radio astronomy is, and then we'll get to the amateur stuff. So,
okay, yeah. So, and I want to find out what happens if if Jodie Foster, contacts if you find any aliens on there. Because wasn't the beginning of Contact, right? She was a ham radio operator. If you saw the movie.
that's it. Yep.
Then I'm going to turn it over. KT4XN. This is Tom Crowley, as he said earlier. He's from Jersey, and go ahead and take it, Tom. Good evening.
Thanks, Rob. Let's see if we can make this work. I guess we put glasses on to see why we're not. Oh, there it is. This will be exciting if I can get it to work. Okay. I'm Tom Crowley, past president of the Society of Radio Astronomers. Oh gosh, we've been in business about 35 years or so. The talk is going to take you through what radio astronomy is, what's been found. Now, if I were giving this talk 20 years ago, I'd set out, and if I were giving it to visual astronomers, I'd say, guys, we've been in business for 25, 30 years, and you've had hundreds of thousands of years to look up at the heavens, and all that you could do is throw queens up there, throw a crow up there, throw a pitcher up there, put a hunter up there chasing a bull, and at the hunter's feet, you put a bunny rabbit. What are you people thinking? Now let's talk about real science. So that's what we'll do tonight. We'll talk about radio astronomy and how it really changed the field of astronomy. I'll give you an introduction. We'll take a look at the electromagnetic spectrum, because a lot of that we may not realize all that's out there and what's happening in astronomy today, that they no longer look in the visual spectrum or the radio spectrum, but they look at the whole electromagnetic spectrum. We'll look at some of the professional radio telescopes, look at some discoveries, and finally, we'll get into some of the projects you can do at home with your amateur equipment. So radio, of course, is part of the electromagnetic spectrum, as is light. When we when we take a look, basically what it is that a photon hits an electron and it kicks off another photon at some frequency. And depending on the energy that it strikes with, depends on the frequency it comes out with. Now, we can jokingly say that radio waves are the slow, easygoing, lazy waves as compared to light or X-rays or gamma rays. So that's kind of one of the things. Here's another look at the electromagnetic spectrum. Hopefully you're able to see this on your screens. But we go from the lowest energy and very long wavelengths. Oh gosh, what is it? 60 cycles we have coming into the house is a couple of miles long.
But Tom,
Yeah,
sorry to interrupt. It's not getting the whole screen. It looks like it's in portrait, needs to be in landscape.
all right. I'm not sure quite how to fix this. Rob, any suggestions? Are you getting some kind of a, let me try this again.
It's like your, I mean, your whole window is like, there you go. Now you got it.
Yeah, when I didn't bring it up
That's
into the
it.
full window. Is that better?
That's it.
Okay, so when we start looking out in space, gamma rays, X-rays, black holes, supernovas, pulsars emit those. We get into the ultraviolet, solar flares, hot young stars can be seen there. The visible, which most people have seen the pretty pictures of visible galaxy stars, planets, the solar spectrum. Infrared, one of the issues with visible is you can't see through the dust, and there's a lot of dust out there. So infrared, you can begin to see through the dust. And then of course, microwave and radio. Cosmic background radiation was found in radio waves. So looking at this, that top image, the black and white image, is the visual image. The bottom image is a radio image looking at our galaxy. So you can see quite a bit more, and things are quite a bit different in the radio frequencies than they are in the visual frequencies. I love this particular image. The top is radio at 400 megahertz. Atomic hydrogen is 1.421 gigahertz. Then radio at 2.7, molecular hydrogen, the infrared. But if you notice each one of these frequencies, you get a slightly different image. Optical, you'll see the black, and the black is just dust in the galaxy and clouds of gases, typically hydrogen gas. X-ray, you begin to see some things. Gamma ray, you begin to see more. And then there's a finder picture at the bottom looking at our galaxy and what's what. Sagittarius is the center of the galaxy. So what causes this, and why are we using radio telescopes? If you go out to the National Radio Astronomy .edu, nrao.edu, there's a lot of great information on radio astronomy. Also, the amateur site radio-astronomy.org is another great place to take a look. So from Earth, we can see from about 15 megahertz on up. And then we can see in the visual, but then most of the sky is opaque to us here. So that's why the James Webb, which will look at infrared, is sitting out at L2 about 1.5 kilometers from us. So radio waves gives us quite a bit of information that we can't get from visual or from the other waves in the electromagnetic spectrum. It basically says the same things, but yeah, about 100 times more observable wavelengths than optical. And in those wavelengths, there's just lots of information. Rob, this picture's for you. There's Jodie Foster taking a look.
Me and Hinckley.
Yep. She's out there at the very large array with a headset on, but she's not sitting on the back of her Chevy in this picture, but she's listening to the little green men. So how did we discover radio astronomy, and who's truly the father? Carl Jansky worked for the phone company, and he was charged with finding why in the radio frequencies, why there was so much static going from the States to Europe. Understand that undersea cable, the voice didn't come into about 1957. Before that, Morse code was used, teletype was used, but voice 57. So any transatlantic phone call in the late 20s, 30s, 40s, 50s was all done by radio. And 2021 megahertz was a big. So that's Jansky, that's his beverage array that he used, that he built. And he put it on Model A wheels. And you can see that going around the track. And then that was pushed around in a circle so that he could look at at that spectrum much in the way that we would turn a beam on a tower. He joined Bell Labs in 28, and his job again was to find what's causing the issues. So there he is with a chart looking at what's happening. What he found in rotating his antenna, if you see on that chart on the right, that you'll see bumps. Those bumps were actually Sagittarius. Now, pretty quickly he realized thunderstorms, distant thunderstorms, but this unknown hiss was what he was trying to figure out. And he spent a little bit over a year trying to sort that out and just couldn't figure it out. The signal didn't repeat every 24 hours, but 23 hours, 56 minutes, which is the time it takes the Earth to make one revolution. So with that, they realized that the signals he was hearing were coming from space. Well, ATT was a little concerned about saying, hey guys, we're hearing little green men in outer space and they're bothering our transmissions. So they kind of put off at making that announcement. Wasn't until 1933 where the New York Times came out with the announcement. Jansky wanted to continue this research, but Bell Labs was satisfied that they found the cause of the interference, and that was good enough for them. So radio astronomy basically died at that point. Young man by the name of Grote Reber built this dish in his backyard. It's a 40-foot dish, and if anybody wants to build it, here is here's his blueprints. So we have a few copies of those, and we have those in a soft copy file. So Grote built this in his backyard. He wrote to Jansky and asked for a job, and of course, ATT wasn't interested, so that didn't happen. He started doing the scans, but what he found out, he was a radio engineer in Illinois, and what he found out pretty quickly was that if he did any observation during the day, there was too much interference from the spark plugs of automobiles. And if you think about that, if you're old enough to remember back to the 50s, we didn't have resistive spark plugs, but we used bare wire. And that caused a lot of interference. I remember hopping up a car and going with bare wire instead of resistive wire. And guy that was following me complained about the amount of noise my engine was making from the spark plugs. What he did was he actually wrote his observations down by hand. He had made 2 attempts at higher frequencies. He finally came down to 160 megahertz and was able to detect the radio emissions from the Milky Way. And the charts that you're seeing, those spikes you're seeing are actually interference from automobiles. And the others are, if you do a scan, that's what you'll see of our galaxy. He worked on this from 38 to 43, did a number of papers, sent them to professional journals, but nobody really caught on. And a lot of folks thought this was just hogwash. But as you can see from the charts that he had sketched out on the right, that he had actually sketched out some of the areas within the Milky Way of the radio emissions. Moving on, National Radio Astronomy telescopes. The Green Bank telescope is the newest in our country. They started building that in the late 80s. They finished it up in the late 90s, early 2000. It's a 100-meter dish. It's located in Pocahontas County, West Virginia. If you're a railway fan, Cass Railway is about 10 miles away. They also have, well, we'll talk about that in a second. The very large array, which are 70-foot dishes out in New Mexico. There's 27 of those dishes. They can put them in several different configurations. And that gives them a tremendous observing area. The latest is Atacama, the large millimeter array. This is looking at much higher frequencies. And that's up at 15,000 feet in Chile. And as you can see, there are no trees. There's something called the Very Long Base Array, which are telescopes across the world. And that gives a tremendous aperture. That in the VLA, when you look at a telescope, you get your resolution from the aperture of the telescope. So the larger the optical telescope is, the better the resolution. This holds true with the radio frequencies, but because they're so long, that getting out to 27 kilometers like the Very Large Array, you need that size to be able to get any resolution at all. And of course, the very long baseline, you can get outstanding resolution. This is looking at the Orion Complex. If you look out tonight in the early evening, you can see this in the western sky. Orion is kind of a new area in our galaxy. The stars are typically between 10 and 30 million years old. There was a cloud of hydrogen gas that has come through our galaxy, and it's called the Gould Belt. That produced a whole lot of new stars and a whole lot of star birthing areas. The Orion Nebula has over 600 stars being born in it today, and they can be detected in the radio frequencies. Chris Dupree over at Agnes Scott has done some studies in that, looking at star birthing in that area. This is the Orion Complex, looking in the radio frequencies. The little green boxes are very hot radio frequencies. And again, these are electrons or plasma, if you prefer, that have escaped. And those electrons will vibrate at whatever frequency they based on the temperature is a way to look at it. And when you look at the professional radio telescopes, their method of measurement is in degrees Kelvin. So we refer to radio telescopes as giant thermometers. This is an aerial of Green Bank. There were 5 or 6 farms that were put together for this. This is the Green Bank telescope in, again, 100 meters. There's an interferometer, and if you take a look in the lower, almost central, you'll see an 85-foot dish. You follow that line up. There's a second and a third telescope up there. And then looking to the left corner of the great big telescope, you'll see the 140-foot. The little building all the way over on the left corner is where the 300-foot telescope was. That collapsed sometime around 1987. It was built to last about 10 years, and it was finished in the late 50s, early 60s. So it had long outlived its planned lifespan. The Green Bank telescope is interesting in that it's much like a DirecTV or Dish Network dish, that it's offset, so there's nothing blocking the view of it. The telescopes that are up there that are in use are a 40-foot telescope that works at 1420 megahertz, which is the frequency of neutral hydrogen, what's called H1, which is typically very cold, between 5 and 20 degrees Kelvin, just above absolute zero. There's a 20-meter educational telescope that can be operated remotely, the 140-foot equatorial mount, and that was an absolute debacle for them to build. They went through many contractors, and a lot of the parts ended up being built twice. And then the GBT, which goes from 100 megahertz up to 70 gigahertz. And now it's actually able to operate at over 100 gig. There's a 45-foot solar telescope there that's also used occasionally. What have we discovered with radio astronomy? Back in the 50s, quasars, quasi-stellar, they looked out there and they saw these things. They were emitting radio waves, but they were very, very distant. What was it? Zenith named its TVs after them. Cosmic microwave background, we'll talk about that. Pulsars, which Jocelyn Bell out of the UK labeled them little green men because they thought maybe it was an intelligent communication. Neutral hydrogen, black holes. Actually, what Carl Jansky discovered was a black hole in the center of our galaxy. That wasn't proven until much, much later. The Navy found out that Venus was hot, and they did that through radio. And then University of Florida did a lot of work with Jupiter and radiation from Jupiter. Some of these are now amateur projects that we can talk about. So temperature of Venus, it was serendipitous. The Navy Radio Observatory found it. And they were seeing more radiation than they expected, and they found the temperature to be 600 degrees Fahrenheit, 320 degrees Celsius. So it was much warmer than what the astronomers would have thought. The cosmic microwave background, first detected in 41. Of course, this is wartime, and it was picked up by the radar, but they weren't concerned about it. They were more concerned about getting the radar to work so that they could see the German planes flying over, attacking the UK. Dickey and Peoples out of Princeton had predicted the cosmic microwave background, and were looking for funding to do a project. Penzias and Wilson were testing a satellite receiver for ATT, and they found 3 degrees Kelvin that they couldn't explain. So Penzias calls his buddy Bernie Burke, who's up at MIT, and talks to Bernie about Bernie's sailboat racing. And Bernie says, well, what are you guys working on down there at the labs? And so Penzias says, well, we're working on a satellite receiver. We thought it was pigeon dung that was causing this problem, this 3 degrees Kelvin that we can't account for. And we sent some guys up to clean it out, but that didn't help. We just can't figure out what it is. So Bernie Burke says, you guys aren't that far from Princeton. Why don't you call Dickies and People, chat with them, because I think you've found what they're looking for. So a week or so later, they made the phone call. They got together. Penzias and Wilson got the Nobel Prize. Dickey and Peoples got a cup of coffee out of it. They were the ones who knew what it was. The interesting thing is that in the Kobe study and more recent studies, they found that the variation in the temperature at that point in time is like 1 in 100,000. So the temperature a little bit after the Big Bang was very, very constant, and we hadn't quite gotten to the point of forming stars or galaxies. The Very Large Array 27, 25 meter antennas, there's 4 configurations I can put it in. It's a resolution that can be up to 36 kilometers. So we're looking at a single dish, 36 kilometers in size is what that means. And its sensitivity would be that of a single telescope of 130 meters. So that site is still quite active. The Green Bank telescope, after the failure of the 300-foot, Robert Byrd, who was senator from West Virginia, got funding to put a new telescope there. Probably about the worst place in the world to put it, but he got the funding, and it operates, as I said, from a 0.1 gig up to 116 gig. Now, to get up to 116 gig, that's got to be an icy cold day in the winter. It's overweight at 17 million pounds. It rotates on 16 wheels. The original plan, each wheel was to carry 1 million pounds. It's interesting when you look at the size of that. There was a storm that came through there several years ago, and I happened to be up there at the time. It was like a tornado had come through, and the telescope, the operator started to put the telescope in its home position, or effectively the position you see now, something akin to birdbath. And as he was moving it, it failed. The generator failed. The telescope took a wind load, not quite twice what it was designed to withstand. It withstood it, and it had no failures and no damage. So that was a pretty amazing feat of engineering in putting that thing together. Again, if you look at it, it sits in a quiet valley. There is in the valley kind of a slot that goes down to Roanoke, Virginia. And some of the telescopes were affected by the airport radar there. So they've kind of blocked out those frequencies. Atacama, up on the plains in Chile, is the newest and greatest, looking in the millimeter frequencies, 66 antennas. They get the equivalent of a 14,000 meter dish, and it's 15,000 meters high. So it's fairly high in the sky. $1.3 billion. We put 500 million into that. And you can see the tractor there that's carrying the a telescope out to its location. So they move them with that tractor. let's take a look at the difference between radio and optical. You take an image with your cell phone, you're getting millions of pixels. And you get fairly high resolution with today's cameras. Taking an image of a deer, that if you look at the actual pixels, they're square. And when you open them up, you can see that. Optical images are pretty magnificent. I have taken a lot of images in the visual frequencies with a telescope and processed them, so you can really get some great images. The amateur today can do as well as better than the professional could do 30 years ago. So there's a lot of work going on in the optical frequencies. I was just out on Maui at working on the Georgia Tech Space Force telescope and updating that with new software and some new hardware. So we'll bring that online in the next few weeks. I've got some more tuning up to do here. The radio images. Radio telescope can take 1 pixel at a time. So how does it do that? If you're old enough to remember CRTs, that you do a scan, that scan would light up one area of the CRT at a time. And you do the scan, and with the radio telescope, you scan in one direction, you scan back, and then you move it slightly and you continue that scan until you get your image. Some of those images take hours, days, and even getting into years to get a full image. For us amateurs, to get a whole sky image, it can easily take well over a year. Radio imaging, the big thing is that with the VL and BA, the very long baseline, and with the VLA, you can get very, very high resolution. And to be able to see a hair at 10 miles is well beyond what the Keck telescope is able to do out on Mauna Kea with 5 milliarc seconds of resolution. So radio telescopes can actually get much higher resolution at a much lower frequency than the optical guys can. What happened? Because we can link the telescopes together, that's how we gain that resolution. And looking out now at space telescopes, there's some that have been out there. For the most part, they've been short-lived. They put one out to look at Jupiter, oh gosh, back in the 80s, mid-80s, and that failed pretty quickly. This is what we see as an amateur, and this is looking at 24 hours. You can see Sagittarius A, which is the black hole in the center of the galaxy. You can see that bump, and taking 1 pixel every 10 seconds and then just integrating it all together. I do that at the hydrogen line, 1.421 gigahertz. You take enough of these charts, you add them together, you kind of get an image like this, and you take that and you put them, and then you span that over time, and over the right ascension declination, you can begin to get images like this. Why aren't we moving? Here's some of the professional images. The hydrogen, the one on the left, hydrogen gas in the arm of the Milky Way. The quasar, the little white dot in the center of quasar 3C 175. You get these radio jets that shoot out that are not seen in the optical frequency, but they come out, begin to slow down, and suddenly you get this mass of photons in the radio frequencies. M81 is a nearby galaxy, and you can look at the hydrogen gas there. There's another 3C288 is a radio galaxy, and you can see the radio jets coming off that galaxy. Saturn you can see, and you can see the arms of Saturn, plus you can see the temperature of Saturn. Neutral hydrogen. This is one of the mainstays of amateur radio astronomy and professional radio astronomy in the early days. I've been able to detect the rotation of the galaxy. You use Doppler shift, you end up making it heliocentric. What that means is you take the Doppler shift that we're receiving here on Earth and you move that to the sun mathematically. And then you can get a pretty good picture of the rotation of the arms. This is kind of an image of what happens. And as you can see, the velocity is 300 kilometers per second. Now that's moving pretty quickly. So we're looking at the arms of the galaxy moving that quickly. On the outer edges, as you get closer to the center of the galaxy, your speeds begin to approach zero. So this kind of talks about what that image was. And running out of time here. So, yeah. Stop hitting buttons. But we're looking at speeds almost 32,000 miles per hour for the speed of the rotation within the galaxy. Supernovas, once a type 1A crushes into a neutron star, it will begin to speed up, much like an ice skater speeds up when they put their arms over their head or and make their bodies a lot smaller. They can get pretty high speeds on ice skates. Same thing happens with pulsars. The pulsars send out through their magnetic beams radio waves, and the radio waves typically, the brightest are in the 300 to 400 megahertz range, but you can see them down at 35 megahertz on up to about 1.5 gigahertz, 2 gigahertz. So, but they're just brightest in the 300 to 400 megahertz. This is kind of what a pulsar looks like. Let me see if it'll move. Nope. But you can see the spin axis, you can see the magnetic axis. If that pulsar, if the magnetic axis is pointing toward Earth, we can detect it, otherwise we can't. So when you think about that, our ability to detect pulsars, we can only detect very, very few compared to the number that are out there. Other radio galaxies, M87 in Virgo A, I believe to be a very, very old galaxy. You don't really see any arms on it anymore. It's 53 million light years away, and its radius at 490,000 light years. I mean, it's a pretty big galaxy. It's a radio galaxy in Virgo, hence it's called Virgo A, and it's a very bright source in the radio frequencies. Black holes, this is interesting. They were predicted back in 1783 by using math. Escape velocity from the Earth among friends is about 18,500 miles an hour. Escape velocity from a black hole, its speed to escape from a black hole is greater than the speed of light. So that's why light doesn't escape. We believe, and we're pretty much proven, there's a supermassive black hole in almost every galaxy. And again, they're created from a supernova collapse, the type 1A. will gobble up hydrogen from a nearby star. It becomes too large and explodes. The sun is a fourth generation star, which means you and I are just made from stardust from 3 other giant stars that exploded before the sun was formed. The radio jets, I chatted about those, 5 light years long. Light year is about a little bit of somewhere around 5 trillion miles long. So these jets come flying out and then they begin to slow down and we detect them that way. You can also detect the transmission out from the photons that are being kicked out. Imaging a black hole, that was done recently with a number of radio and optical telescopes, but we've always been able to see the accretion disk around the black hole. So the new optical is pretty special, but in radio, we were aware of it and we could see the accretion disk is the star in the dust, the stars and dust that are circulating the black hole that at some point in time will fall in due to gravity. Let's take a look at some amateur projects. What do you need? Some electronics being hams, you have that. What are your interests? What do you want to do? How much money do you have to spend today? It's getting cheaper and cheaper with the advent of the SDRs. Typically, buying a radio telescope receiver was $2,000, $2,500. Now, the SDR play for a couple hundred will do a great job. And again, radioastronomy.org is the Society of Amateur Radio Astronomy website. Lots of good information there. Looking at radio projects and the sources, I'll just leave this up for a second. It's a lot of information to go through. FM, well, in HF, Jupiter and solar, 18 to 30 megahertz. We'll talk about Jupiter in a minute. Solar right now, with the advent of cycle 25 coming up, that if you, during the day when you're not using your radio, you can set it just below 15 meters, find a quiet spot and point your antenna to the south if you have a beam, and you'll be able to see there's a program called Radio Skypipe that's free. You can get that and you just plug the sound, your receiver output into the sound card. And if you see something, you'll see it. FM media detection, simply looking for medias falling in, looking at an FM station about 500 miles away. You can spectral scans. Again, I did H1 with a Doppler shift. A lot of the guys have detected the satellites that are out there, the ones that are going out. I, for students, build something called an itty bitty telescope. It operates about 12 gigahertz, and it can see the sun. It'll see the 300 degrees Kelvin of you and I or trees. So it's a good educational telescope for kids to get them interested in science. Whistler radio, that's a listening to the earth and the sounds from the earth. Typically there's a thunderstorm going on every moment of the day somewhere near the equator, and there's radios that you can get. You're typically looking 20 to 100 kilohertz. So you'll see lightning or solar flares, that kind of thing. I'll stop touching things. So here's some whistlers that have been recorded. It's kind of interesting. There was a project in Huntsville that we had talked to the Huntsville folks that they wanted to correlate the whistlers with the space station and what they were seeing and hearing. Actually, what they were seeing. That project never really took off. There was a couple of guys that worked on it. Solar flares. It takes about 100,000 years for that nuclear fusion happening deep within the sun to come out. And the red that you're seeing are the solar flares as they come off. And they're hundreds of thousands of miles above the surface of the sun. Of course, as you know, during the day, this changes the D, E, and F layers. As we're getting more active with cycle 25, 15 meters and 10 meters are beginning to open up. Sudden ionospheric disturbances, SIDS. You can look at this at very low frequencies. We, in conjunction with Stanford University, build a device that we sell for about $80 that looks at transmissions to submarines somewhere between 20 and 50 kilohertz. The station that I use is 24 kilohertz from Cutler, Maine, and that sends transmissions out to our submarines. And I'm sure at the moment it's quite busy with transmissions. Radio flares can, are typically X-ray flares. But what happens is that if there's a flare, most typically it will also produce signals at lower frequencies, whether they be infrared or radio frequencies, and that's pretty much how we can detect them. This is looking at the Stanford project, and this is a quiet day. You see 7 a.m. coming up with the signal level increasing out to when the sun goes down. There's several flares here that you can see with the dropouts. There were 1.6 and a 2.3 flare, the 1.6 being the smaller on the left. So as an amateur, you can actually do fairly decent science. This information is collected by Stanford University. Here's another solar flare with a pretty good dropout. Other projects, meteor detection, Jupiter Radio. Radio Jove is a NASA project where you can operate typically just below 21 megahertz is a good quiet area. Gamma ray burst, some guys are playing with that. That's a tough one. Some of the guys with larger dishes have been able to detect pulsars. There's a guy in Texas and there's a group in Germany that are very good at that. There was a gentleman in Germany who was able to see the CMB. And interferometry is where you take 2 or more radio telescopes, put them together, and you increase your signal and you decrease the amount of noise that you're seeing. Meteor detection, again, you're looking for signals to bounce off either aircraft or meteors, and you're detecting that. Very simple project with an FM radio. There's a group in Canada that does this for the school kids, and they've found that the 10, 15-year-old Chrysler radios to be the best. It's basically more of the same. I've played with it with the Radio Shack FM antenna pointed to an FM station about 500 miles away in the Midwest. So you kind of get a burst of information from the FM station. Some garbled sound is about all that you hear. Charting it, this is what you can see, doing a spectrograph of it. Jupiter radio, as I said, 15 megahertz to 28 megahertz. 21 is really the sweetest, just below 15 meters. There's two types of bursts, the L burst and the S burst. The L burst is based off the magnetic poles of Jupiter as it spins. L burst is in interaction with the Jovian moon Io, and you'll get a short burst, which is a kind of referred to as the sound of a machine gun. The long burst is more like the ebb and flow of the ocean on a rocky beach. Lots of work being done there. Again, if you look up Radio Jove, it's a NASA project, and they have finished building their last Jove receivers, and they are now looking to redo it with SDRs, low-cost SDRs. I'll just get through these. Interferometry, you put two telescopes together, and they add and subtract, so you actually get a greater signal than a single telescope, but you also reduce the amount of noise you're receiving. So it's kind of a more advanced way to do it. As technology improves, our costs are going way, way down. Society Amateur Radio Astronomers is selling a 1420 telescope complete for about $250. It uses a 2.4 gigahertz dish along with a small SDR, and it actually works quite well for detecting neutral hydrogen. That's it. Questions?
Not a question, but great presentation. That was really good.
Thanks, Ade. It's a little difficult without looking at folks. And I hope to see you tomorrow. Well, folks, thank you so much for inviting me. I've really enjoyed giving this. I hope you learned something and that you can do some searches on the internet and kind of increase your knowledge. Rob, I'll send you this presentation.
I'll post it.
Okay. Thanks, Guy.
Appreciate it.
Thanks, Tom. All right. Let's see. Ade, do we have a any sort of a membership report or finances?
Well, we have currently 74 active members. The number goes up and down a little as renewals and new members come and some memberships expire. Finance-wise, we've got about $17,500 in liquid assets, and some of that is about $700 of that is in PayPal, so it needs to be transferred over. So hanging in there.
All right. Yeah, we're working on Skip and I in particular working on inviting new folks to the club. So we're getting some success with that, sending out letters and inviting people to events and things like that. So I think next year will be much better. Well, the rest of this year we should grow quite a few members, I would think. We've got quite a few. Does the 70, does that include the free membership, Said?
Yes,
Okay. I know we've added quite a few of them recently.
just added one today.
Yeah. Okay. All right. Well, let's see, Steven's gone. Jeff, you got anything for the club?
No, not tonight.
All right. Thanks for stepping in with my emo problems the last couple of days. I think I've got that
You
somewhat
got
mastered.
everything squared away?
Yeah, I think I've got it mastered and figured out I was playing with it. So thanks.
Absolutely.
Yeah, sorry it took me so long after 2 or 3 times you've explained to me. So
No, it's all good.
yeah. How's the Nano working out for you? Have you had a chance to play with that?
Yeah, a little bit. They're still confusing, but it's nice having the one with the larger display on it.
Good, good. All right, guys. Well, like I mentioned, the WSB event's coming up, so take a look at that. Look at the schedule. It's there's a little link at the bottom of the page on the website. There's a link at the top right-hand corner of the website you can click on that. It'll take you to the WSB event page, and down at the bottom there's a link to that to take you to the sign-up page where you can actually pick a couple slots to work the event starting next Saturday. So not this Saturday, but next Saturday. So consider taking advantage of that and helping us out with that. So anything else, Rob?
No, it's going to say check the website, groups.io. We let everybody know everything on groups.io. And we're on Facebook, and we're on YouTube, the Atlanta Radio Club YouTube channel. This presentation will be available on YouTube in a couple of days. I'm not as fast an video editor as I like to be. Plus, it takes a long time to upload these large files. It's probably my Wi-Fi, but should be couple of days. And yeah, lunch tomorrow, and the event on Saturday, right?
Yeah, and hopefully we'll get some good news from the Red Cross here soon, and we'll continue to obviously continue to implement Zoom into our meetings too. I think that's a great tool to use. So hopefully we'll be back to some in-person meetings here soon at the Red Cross. So keep an ear out for that. If nothing else, I guess we can close the meeting out. And thanks again, Tom, for a great presentation. Do we have a meeting subject for next week, Rob? I mean, next month?
Not yet.
Not yet. Okay.
Not yet.
All right. All right, guys. Well, if nobody has anything else, y'all have a wonderful evening, and do join us this weekend, tomorrow for lunch, and Saturday for the day at the park out at Brook Run in Dunwoody, noon to dark. So look forward to seeing you there. Y'all have a good evening, if nothing else.
Thank you, John.
All right. You have a good evening.
Thank you.
Thanks, John. 73, everybody.